Okay. Firstly, thank you so much for having me here, and it's also a great honor to be going after Dr. Chung. We definitely had a lot of fun being in the DARPA challenge as well. And it was, I want to touch a little bit on that first, but overall I want to be talking about field robotics for space robots. But I want to start by bringing that back to Earth, and specifically under the Earth, by talking a little bit about the DARPA Subterranean Challenge. JPL, the NASA Center in Los Angeles, was the lead team in Team COSTAR, collaborating with Caltech, LTU, KAIST, and MIT. It was an honor really to be a part of this great competition, which I think was a fantastically designed event to really push forward field robotics by what it was requiring, so that instant performance you needed in that 1 hour for the competition in what could be any variety of underground environments. And what we learned is that there are a lot of underground environments. They're very diverse. And so really what it pushed the teams to do was to do a lot of field testing. So this is a representation of some of the field test sites that we had around the US and some field test sites overseas in our team. And it ranged from things like mines underground, 800 feet underground, coal mines, different types of urban environments, including this abandoned substation, power substation, and different types of cave environments, lava tubes in Northern California, and different limestone mines. And really, the goal is to go to as many representative underground environments as possible to try and find different details of what the robots can and can't do. And so we went to 27 different field sites over the 3 years and over 150 different field tests to really test a variety of robotic systems. And I really label it as the quest for the unknown unknowns. We're really trying to find what conditions reveal something that we didn't previously know, and so we can work on it to improve the robustness of our robotic system. And so that's things like the vertical shaft that Dr. Chung was presenting, different types of thickness of mud, different types of rocks in caves, different obstacles that you see around, different types of slopes, stairs, and the variety of different stairs. Tried to test each of them so we can learn more about what are the challenges that we need to work on, because we don't know them beforehand. And so that's going to high schools, which have different interesting geometries and stairs, going to abandoned buildings that have some very different types of areas to navigate through. It's going to abandoned subway stations. It's going to different types of caves. This is the limestone cave, which is different to every other environment that we've been to. And then to limestone mines, which are simpler in some areas, they're really challenging in some areas, but their scale is immense, so there are many, many kilometers to explore. And so you see our multiple robots exploring that. So we really learned a lot from this, and it was incredibly valuable to our team, really just pushing to test as much as we could. And I wanted to touch on a little bit of lessons learned from the extremely intensive field test campaign required for Sub-T. And then we can, I realized my video wasn't on, I apologize. And then we learned a lot from that, and I just thought it'd be useful to share those details with the community here. So firstly, when we're trying to test some of our VIO systems, we wanted to test in dark environments. We wanted to use OptiTrack or Vicon to be able to track the ground truth of what we're doing. And we realized that doesn't work very well when you're trying to simulate a dark environment because the lights that are used there, even if they might be in a non-visual spectrum, they tend to show up in our sensors. And so using this type of ground truthing underground is very difficult. So we found actually using some type of highly detailed kind of survey profession scan, and then using that to do robot sensor to high resolution map matching was the best way to get ground truth data. We found having a really well-engineered base station that was robust, quick to set up, had backup power, and was very capable was an extremely useful asset to be able to have a really solid platform that can be used to debug and control all the robots that you're operating, and very easy to deploy. In some scenarios, we found when you're really going towards the edge of uncertainty in different environments that is very different to what you've tested in before. Where possible, it's good to reduce the risk. So here we've got a pulley system, a kind of safety backup system for the Spot robot when we were learning how to autonomously do stairs. You change the wrong settings, it can be a little bit disastrous. And so we want to implement this safety system until we got confident with how the robot would handle those stairs. Also, I'm sure familiar with many people, radio frequency or electromagnetic interference can do some weird things. Here's a bit of a fun example where using our walkie-talkie radios would scroll our UI to kind of zoom in and out for what we're looking at. But we also had some other really actually impactful issues where it was causing mechanisms to move at the wrong time and causing issues with cameras and different things like that. So it's definitely something to always keep in mind if something weird's happening, to kind of look at that and try and really work on your different shielding that you have. We went for a large robot team, partly because of what Dr. Chung was saying of having the heterogeneity, but also expecting that you're going to have robot attrition. And also we were expecting quite large scale environments, and we were testing some large scale environments. And our strategy for that environment was to have many robots exploring different areas. And so it's a lot of equipment, a lot of robots to prepare, and it made us realize that it's really important to be able to plan ahead of how you're going to coordinate these robots. And so we had our own trailer, which is what you see here with, I think there's 11 robots there. 3 of them are drones in boxes you can't see, but there's 4 spot robots and 4 husky robots. But this is our own trailer, and so we could plan it out. We could spend our time making sure that we knew how we're going to fit them in, knew how we're going to properly secure them, as well as secure all of our equipment. And just another shot of us coming back after the competition where we had 5 spots, 4 huskies, and a set of drones. So a lot of equipment, but it takes a bit of time to pack in, but having experience with doing that in your own system, where we had our trailer and our truck, was something that was really important to safely get our equipment where it needed to go. We also had a large team of people in the field for a long period of time during a pandemic. And I think it's quite a unique situation where obviously safety is paramount in a lot of what we do in a field test, but safety in a pandemic is another thing entirely that adds multiple layers of consideration when we're planning a field test. And so I wanted to go through some of the things that we learned from doing that hopefully people don't have to do that too much going forward, but just some interesting insights to how to coordinate it. So we had up to 50 people in the field at one point in time, and obviously many robots there. So some things that we were doing to make sure people were COVID safe, and thankfully, or not thankfully, but we were putting as much as we can in place that people wouldn't be catching COVID, people wouldn't be getting sick, and we were successful in doing that, which was great. And so here we're doing some drone operations, so you can see the 2 different netted areas that we have for people being safe from the drones. And really the lesson in general for keeping people safe is try and make it as easy as possible for them to do that. So we had regular COVID testing where we'd bring people to the venue to test our team, obviously making sure people are wearing masks and keeping socially distanced, having places people can eat that are outside and spread out so people don't have to be near each other. But for here, when people might want to be watching the test, we need to make multiple areas so people don't crowd together to watch what's going on, as well as obviously being somewhere safe from the drone. We also set up a kind of mirroring projected of the operator screen. So people who want to watch what's going on don't crowd around the operator screen. Obviously, this is when we're not flying drones, and they can stand around safely to be seeing what's going on. Also, one of the things that is important is for team meetings, having a megaphone. So you're not all crowded together to listen to the person talking. You can stay socially distanced. And really getting really clear buy-in from people of the importance of what they're doing so people can take responsibility for that. So even though we had a large robot team that was hard to manage, it was also a big task managing the large human team to make sure everyone here was safe. And this is kind of the maximum team that we had there. Not all in the final competition because there's other teams in there, but around the venue as well. And so in our quest for the unknown unknowns, it was, again, an extremely valuable experience that was beneficial to everyone involved, being involved in the Subterranean Challenge, but also valuable to advance the technology that NASA thinks we need for potential future missions. And what was great about it is that we were able to go to real underground environments to get conditions that were true to what we expect to see in underground environments, or whatever we thought Dr. Chung would throw at us, and it was an incredible course that they did throw. But what about Mars? how do you know what you're going to go and test on Mars? How do you go to a real Martian environment without actually going to Mars? How do you prepare for that? Now, okay, you could say maybe we've had previous missions there that we can learn from, but what about something like Europa, a moon of Jupiter? We've never had anything on the surface before. You have some satellite imagery, which you could learn from, but we can't go there and do a short-term test. Or even the underground on other worlds, on Mars or on the moon. We might have an idea of what they're like, but we've never been there. We can't actually go and visit that. We can't go and test representative underground environments because it's on a different planet. And so for space robotics, I want to stress that when you have something like this Mars rover, $2 billion rover that gets onto Mars, its first time that it's in the true field of operation, that it's truly in the field where it's supposed to be deployed, the very first day is the first true field test. And it's its only field test, and it's never coming back to the lab. And so really, we need to find these unknown unknowns before launch as much as possible. There is some we can do once it's on a mission, but there's a limited amount. We can't go and do repairs, we can't change parts, can't repair mechanical things. And so it's extremely important to try and learn as much as we can beforehand so that when it actually hits the real field, that we can be as successful as possible. And so the ways we do that is to use the best knowledge that we have of the environment. And a lot of that is based on the current scientific knowledge of what the geology is, what the environment is, what the atmosphere is, from whatever observations we can make from Earth or from previous missions. That's kind of the core of what we have. And that's, that could be flawed and that could lead to some issues, which has happened. But that's the starting point. And then we design component tests. These are tests of different components of the system in different components of the expected environment, as much as we can reproduce. And then analogs, finding places on Earth that match as much as possible the conditions we expect on these other worlds. So firstly, let's look at component tests. And let's take Mars as an example. What are the components of Mars that we care about or that are important for robotic testing? So there's the temperature, there's the atmosphere, the pressure, the density of the atmosphere. There's the radiation environment. There's the different types of terrain and the visual aspects of that terrain. And then there's the acceleration due to gravity. And so for component tests, some things are reasonably straightforward in the fact that we take different parts, different subsystems of the robot for radiation, and we put them into a radiation test, some type of chamber environment where we subject them to the expected radiation and see how they perform. Similar for temperature, and then often we do temperature and pressure in the same way, and this is something in a thermal vacuum chamber, such as you see here is a 25-foot thermal vacuum chamber at JPL where we can fit a full Mars rover in, and that can be pumped down to a full vacuum and then filled with CO2 to the same density of Mars atmosphere, which is about 10% of what we have on Earth in terms of the pressure, and then made to match the temperature, as well as having effective solar radiation coming in to have differential thermal heating with a big light source coming from the top. And so this again is component test. Well, this is the full system, but testing some components of the conditions. Also for terrain, we look to find ways we can test what we expect for the terrain based on geological understanding and previous observations. And we have the Mars Yard for that, where it's set up to have different slopes, different types of terrain, from the more slate-like terrain to dirt to sand. You see we have one of our surrogate rovers here that's doing some ground testing of different instruments on this terrain. But also you see there's this weird-looking rover system on the right-hand side. And that's because Earth gravity is about 3 times that of Martian gravity, or the acceleration due to gravity. And so we want to combine the types of terrain, especially for something moving over the surface, with the same acceleration due to gravity. And that's what this platform is for. This is called Scarecrow. And really, it's designed so it's the equivalent weight that the Mars rover would be on Mars. So that means much less mass than what it actually is, but then the same mobility system, so that you can test how that's actually going to work. And so really the way that we can try and do field tests to prepare and make sure the system is ready for the ultimate field test that we can't come back from is testing the combinations of the component conditions, us replicating them, and then the component subsystems that we can test in those environments, and trying to build up to have those subsystems be as close to the full system as possible. But really the challenge here is that we are replicating the component conditions that we think will exist, which doesn't really allow us too much to find those unknown unknowns. We can find a little bit in how our system reacts to those conditions, but maybe there's some things that we don't expect that we haven't planned to test for. And so we still want to find as much of these as possible before launch, and that's where analogs come in, where we try to find real environments on Earth that match as close as possible to what we see on Mars, and to then go out and do analog testing there. And so, for instance, for the different terrain that we might be looking at, there's lots of nice deserts in California. And so we go out to the Mojave Desert and test this scarecrow platform on different types of terrain. In this case, it's going over sandy dune terrain, testing how the full mobility system is going to be working there. And that gives a kind of greater confidence, but also learning and ability to try and find some of the unknowns. Another thing that we can look at is the atmospheric conditions. So again, the Martian atmosphere is about 10% of what we have on Earth, but we can find that by going to a high altitude on Earth. And so, for instance, when we're testing the entry, descent, and landing system, which you can think is an aerospace thing, but it's all autonomously controlled, so it's just a robotic aerospace system. And so this is the testing that we do. We launch a rocket that is going to be carrying this system for testing a parachute deployment. And that, as we launch it, it's going to be going up to high altitude where the atmosphere gets thinner on Earth, so that it replicates roughly the density that we have on Mars. As it gets basically to space, it then tests the deployment of this parachute. And repeated tests in there to test different technologies, different designs, to make sure we can be confident that it's going to be working in the conditions. So we find those analog conditions on Earth and do the tests there. That's kind of the start of the entry, descent, and landing phase. Another important part, which is touches on some more robotic technology, is how we look at the terrain visually to track how we're moving and divert away from obstacles when the rover's coming down to land. And so for that, we look for similar visual environments as you're looking down. And again, we look at deserts nearby in California, and this is looking in Death Valley. And we just care about the vision system for this component test in the analog environment. And so that vision system is mounted onto a helicopter. So a bit easier to fly and operate and control. And then that helicopter is flown over the representative environment, and the full vision system is run to be tracking the terrain, looking for hazards, tracking its state, and then seeing how that would be used to control the spacecraft to divert. And so you can see some examples of that here. Or just the same thing, but just showing how the helicopter is moving around and setting up for that. So again, this is only a component of the system, but it's going to as much of a real environment as we can get for the types of environments we're looking for. So you can see the feature tracking there and analyzing the terrain, just like they might be doing when the rover's coming down to land. So what we've been describing there for the Mars rover example is for quite a mature system where we're looking to prove out and verify that each component is going to work when it gets to Mars. And those analogs are very useful to prove that out and to again, identify any issues that may come up. But also JPL and NASA in general is involved in developing the technologies for future missions. And that earlier technology development is something that can really use analogs a lot more to do that search for the unknown unknowns. And this is really where the subterranean challenge fits in for JPL, is that it's a fantastic way to advance the technology for future missions exploring underground environments, where it really allows us through the kind of large field test campaign to learn a lot and advance the technology a lot. So some examples here of different things we do is some targets that we may think we want to explore. So this is in Mars, there's these features called the recurring slope lineae. That's these black streaks that you see here that change seasonally, and that we think they're indicative of some type of flowing water. And so it's an interesting area scientifically, but this is a side of a cliff. So a traditional rover is not going to be able to go there to take measurements. So knowing that's of interest, we look for analog environments on Earth and then go and do field tests there. And so there's things like rock climbing robots on the left, which have the little micro grippers attached to the wall, and then abseiling type robots. And then we find representative environments and go and test these systems, learn what works, what doesn't work, what we need to improve in the systems and the autonomy to go forward. There's things that we haven't been to before, though, and that we don't have that much information on, such as Enceladus, a moon of Saturn. And this is an icy world that's thought to have a subsurface ocean. It's got high temperature, water steam gauges coming out from the surface. And it's a fantastically fascinating place to explore. But it's an icy world with some really interesting terrain. And so we find analogs on Earth to test our robotic systems of how can we move over this terrain if we were to have a mission there. And so we go to glaciers. And so this is an example of a wheel-on-leg system being tested over a glacier in North America. And this is testing the different mechanical systems, but also the different kind of software systems, the algorithms of how we're going to do this different types of mobility over terrain that's quite challenging to make sure we can get a scientific instrument to where it needs to go. And finally, caves on Mars. Now, a lot of the caves that we see on Earth are dissolution caves, so it's from water that's coming through and dissolving the rock, and often that's in something like limestone. We don't think that's on Mars, though, because limestone is left over from ancient sea life, and water needs to be constantly coming through and cycling through to dissolve these environments, and we don't see too much of that on Mars. So really, we look for geologically formed caves from volcanic activity. And these are lava tubes. And on the right, we see some satellite imagery that indicate kind of a linear pattern of some collapsing of a lava tube, we think, which gives us fairly high confidence that there is a lava tube cave on Mars. And that's where kind of the real kind of application of the technology from SubT goes, of having robots that can explore these lava tubes environment. And so we've been doing a lot of testing in analog environments, which is lava tubes on Earth. This is particularly in Northern California. And it's not just testing the robot technology, not just testing the robot autonomy. It's also testing the operations that we would use to do an exploration mission. So it's an autonomous robot. It's doing all the things it would be doing in SubT, looking for things of scientific interest rather than objects for search and rescue, but also thinking about how do we include the scientists, how would we run the mission to be able to get the scientific information we want in the context of a real mission. So it's looking at the combination of technology and the concept of operations, the actual execution of the operations, and learning from that in these analog environments that we are doing a lot of. So I think I don't have too much time left, so I'll just go quickly though through one more case study of how we can use analogs to test. And this is an interesting one because it's kind of the first of its kind is the Mars helicopter. First powered flight on another world. And so this is going to be a bit of a sketch of some of the testing done to prepare it for its first ever field test. If we say this circle is flight on Mars, of all the different components it involves, all the different aspects that would mean you're actually flying on Mars, we try to look to replicate certain parts of it. So we can look at the realistic aerodynamics, we can look at the aerodynamics and realistic gravity acceleration, and then also using visual navigation with those. We could look at having the realistic visual environment and then having realistic lateral translations that we want to have. Unfortunately, on Earth, we can't test all those together. And so we have to have separate tests for each of those. So for instance, realistic aerodynamics, same vacuum chamber we've been talking about before. Initial test is seeing can a helicopter produce lift? And that was a confirmation that yes, it can produce lift with the appropriate revolutions per minute and the appropriate geometry of the blades. So then the next test is, can we do realistic aerodynamics and gravity environment? Same vacuum chamber, but this time flying with a light weight, so a low mass, so the weight is equivalent to what we'd have on Mars, and seeing, okay, we can get lift, but can a human fly? And the answer really was no. And the unknown learned there was that control is very difficult in a low density atmosphere. You lose a lot of the damping you would have otherwise. So really you need responses much quicker than what a human can have. That lesson was learned and developed to the next version, which is testing the same vacuum chamber. This time it's roughly the same mass as you would have for the actual flight version, but you can see there's a cable here at the top, and that cable is providing the offload of the mass, of the weight, for it to be able to fly. So successful, but those who are really pushing to get out of the lab will notice the Vicon cameras and the Vicon dots. This has been controlled through a Vicon in the loop system. So it's just testing the dynamics there. So next step is let's do visual navigation in the loop. And so the same test was done, but with, again, something that's often used in the labs is just artificial features for tracking in the vacuum chamber, but this is with a visual navigation in the loop. Of course, we'd like to have real visual environment down there, but this is as close as we can get in the vacuum chamber. That's quite a high value asset. Now, also, you can see the size of the vacuum chamber here. It's impressively large, but it's not really somewhere where you can do large lateral flights. So that's something that's out of the bounds of what we can do in these Martian atmosphere gravity offload tests. And so separately, the team was doing field tests in realistic environments with the vision system and testing the visual feature tracking system, testing the full visual navigation system on a surrogate helicopter or a surrogate drone also. And then for realistic lateral translations, that's something, again, that was done in that test, but hard to do with all the aerodynamics. And so really simulation had to be used a lot there to try and learn more, but we all know there's some limitations of simulation there. However, through all this kind of combination of piece parts to try and test as much as possible, we know that it was successful in its first ever flight on Mars. And subsequently, it's had many flights, some translating up to 600 meters in a single flight. And it's been, the team was extremely excited to see it kind of released from its confines of a vacuum chamber to be doing what its actual mission was. But it's always incredible to me to see think that these flights were the first time it was properly flying in the designed environment. It's never done that before. And it's been incredible the success that it's had in doing that. So with that, I'll wrap up. I think I'm a little bit over time. Thanks for this opportunity, and good luck to everyone else in your quest for uncovering the unknown unknowns and improving the robustness of your field robots.
Thank you, Ben. Does anyone have questions for Ben? So we do have one in Slack, so I'll read it out. How many unknown unknowns have been identified and answered before you and your team were sure that the system was ready for deployment?
Which system, I guess? So for sub-T, lots, and it never stopped. For the Mars rovers, I think countless as well. I don't have a good number on it, but it's an ongoing process. Just like it with a lot of robots, you find something that's an issue, you try and dive down into it, solve it, and you come into the next issue. I think like hundreds for sub-T. For the other systems, if it's more mature of a system that we know a bit more, it's hopefully less of those. Like each kind of major subsystem test may uncover a handful. And it's really based on kind of the engineering judgment of the team to say what gives them sufficient confidence that it can work, and that's really comes into the design of the analog test and the component test. And if we find something that we don't expect, it's kind of going back around to make sure that we can successfully pass that test.